9th of March, 2020. The world's clearing houses sent out margin calls totaling $140 billion. In one day, not a loss, not a bankruptcy, a demand for cash from people who were, on paper, perfectly solvent. Everybody had the money. Almost nobody had it that morning. And that gap is where the mathematics gets strange. Because a margin call is not an event. A margin call is a phase transition in a fixed point equation. Let me show you what that sentence means. Start with something you can hold in your head. 3 banks. AOSB 90. BOC 90. COSA 90. That is the entire economy. Is anybody in trouble? Obviously not. It is a circle. Everyone pays 90. Everyone receives 90. It nets to 0. But look closer. I can pay only because C pays. C can pay only because B pays. B can pay only because A pays. Nobody in this circle has any money. They have the promise of money, arranged in a loop, and the loop is holding itself up. And notice what we just did. We did not calculate those payments. We assumed them, then checked that the assumption was consistent with itself. That is not arithmetic. That is a fixed point. And once you see it, you cannot unsee it. Let's make it precise. In 2001, Larry Eisenberg and Thomas Noe wrote down the model that basically every systemic risk regulator on Earth now runs. Every bank gets an amount of outside cash, EI, real money from outside the network. Total obligations, P bar I, and pi J, the fraction of bank I's debts owed to bank J. Now the only behavioral rule in the entire model, and it is almost insultingly simple. Every bank pays everything it can up to what it owes. Written down, PI equals the minimum of P bar I and EI plus the sum over J of pi J, I times PJ. What you pay on the left, what you receive on the right. The unknown appears on both sides. That is the whole subject. You cannot isolate P because P is defined in terms of itself. What you have instead is a map. Feed it a guess about who pays what, it hands you back a new guess. Call it phi. A clearing vector is AP with phi of P equal to P. A fixed point. Does one exist? Yes, and the reason is beautiful. Phi is monotone. If everybody pays more, everybody receives more, so everybody can pay more. And the space of payment vectors is a complete lattice, a box from 0 up to P bar, closed under maxima and minima. Knaster-Tarski proved in the 1920s, with no analysis, no continuity, no topology, that a monotone map on a complete lattice always has a fixed point, and that the fixed points themselves form a complete lattice. So there is a greatest clearing vector and a least one. Read that again in money terms. The amount of money in this system is not a fact you look up. It is the solution to an equation the system is solving about itself. Greatest and least. If those coincide, fine, the world has one answer. And they do coincide whenever the network is regular. Meaning every cycle of debt contains at least one bank holding real outside cash. Take that cash away. Back to our pure circle. E equals 0 everywhere. Now both of these are perfectly consistent. Everyone paying, where nobody pays anything. Same balance sheets, same contracts, same law. Two worlds, and the mathematics does not prefer either one. Nothing has to happen to move from the first to the second. No fraud, no losses, no bad news. So how does it land? The algorithm is chilling in its simplicity. Assume everyone pays in full. Check who cannot. Those banks default, recompute everybody's income. Check who cannot pay now. Repeat. It is called the fictitious default algorithm. It terminates in at most n rounds for n banks, and each round is a wave. You're watching a cascade converge. So far we have pretended we know the network. We do not. Nobody does. The interbank graph is private. It rewires daily, and no regulator has ever seen all of it at once. So we do what physicists do when they cannot see the microstate. We go statistical. Forget the specific graph. Keep only the degree distribution, pk, the probability a random bank has k counterparties, and encode the whole thing in a generating function. G0 of x equals the sum over k of pk, x to the k. This object is a magic trick. Its derivatives at one hand you the moments. And you need a second one, because if you arrive at a bank by walking along a link, that bank is not typical. You're far more likely to have landed on a hub. The degree of a node reached along a random edge is size biased, and the generating function for that node's other links is g1 of x, equal to g0 prime of x over g0 prime of 1. Now the definition that matters. Call a bank vulnerable if losing one single counterparty wipes out its capital buffer. 1. Contagion is then a branching process on the vulnerable banks. A failure hits its neighbors, some fraction of those are vulnerable. They fail, they hit their neighbors. Let you be the probability that one branch of that cascade dies out. Self-consistency gives you equals g1 of u. Another fixed point, exactly like our clearing vector. And this one has a phase transition. U equals 1, extinction guaranteed, is always a solution. It stops being the only solution the instant the derivative of g1 at 1 climbs above 1. Expand that, and everything collapses to a single line. Sum over k of k times k minus 2 times pk greater than 0. The mean of k squared exceeds twice the mean of k. That is the Molloy-Reed criterion, the closest thing finance has to a law of nature. And look at what is steering it. Not the average number of connections. The second moment, the stability of the entire system is decided, almost entirely, by its most connected institutions. If the degree distribution has a fat tail, if the exponent sits below 3, the second moment diverges, and the criterion is satisfied always. At any density. Forever. There is no safe average in a scale-free banking system. Here is where it gets perverse. In 2010, Prasanagai and Sujit Kapadia ran this machinery on interbank networks and plotted the probability of a system-wide cascade against the average number of counterparties. Common sense says that curve goes up. It does. Then it peaks. Then it falls off a cliff. Two forces are fighting. More links means more channels for a failure to travel. But more links also means each exposure is smaller relative to capital. So fewer banks are vulnerable to any single neighbor, and eventually that wins hard. Between them sits a window. Inside it, the probability of contagion is tiny, and the size of contagion, if it fires, is close to everything. Robust yet fragile. The most dangerous shape in economics because it is indistinguishable from safety right up until it is not. A semiglue, Ozdegler and Tabaz, Salehi sharpened it in 2015. Below a critical shock size, connectivity is insurance. Above it, connectivity is the transmission mechanism. Identical network. Opposite sign. Now put the two halves together and watch what a margin call actually is. It does not change the graph. It does not change who owes what. It changes exactly one vector. E, the outside cash. It reaches into every balance sheet at once and subtracts. And in the clearing equation, E is precisely the term propping the fixed point up. Lower E, and the box of possible payment vectors shrinks. Some banks slip below the minimum. The algorithm runs one extra round, then another, and the greatest clearing vector, the good world, the one where everyone pays, slides down and, at some threshold, stops existing. What replaces it is not a smaller version of the same thing. It is a different fixed point. That is the whole event. Not a decision, not a panic, not a villain. A monotone map on a lattice, resolving itself under a slightly smaller constant, landing in a different basin. $140 billion of demands went out that day, and every one of them was legally correct, individually reasonable, and priced by a model that never once looked at the second moment of a degree distribution. A year later, Archegos cost its prime brokers over $10 billion in 3 days, 5.5 of it at Credit Suisse, for the same reason. Everybody had margined their own exposure. Nobody had margined the fixed point. So, the thing to walk away with. When you hear that a firm ran out of money, that is almost never what happened. The money was never a quantity. It was a solution, and solutions can vanish. Previously, we found curvature hiding inside an exchange rate. Arbitrage as holonomy. Subscribe to unravel the invisible structure with the margin call.